Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we continue the discussion on impedance matching. We first consider the case with impedance matching using transmission lines. These are the distributed circuit matching networks that I talked about in the previous module. Okay, let's get right into impedance matching using transmission line. Suppose we have a transmission line, okay, with a characteristic impedance. We will assume again lossless transmission lines, okay, and one of the reasons why we assume lossless transmission lines is because the matching network itself needs to be lossless, and then connected to a certain load ZL. You might have a source whose impedance is Zg connected to a phasor voltage Vg. As I said, the goal of the transmission line in the previous module, as I said, goal of the matching network would be to have matched the impedance of ZL to Zg. Okay, it is not the goal to match ZL to Z0 or Z0 to Zg, while that is also a very important thing. That by itself does not give you maximum power transfer, but goal is that you match ZL with Zg. Again, to match ZL with Zg, I need to know that ZL, or I need to make the condition equivalent to ZL complex conjugate or ZL conjugate to be equal to Zg complex conjugate, right. So, this is the condition that I am trying to achieve. For now, let me consider only real cases, that is, I consider both ZL and Zg to be composed of two resistances Rg and RL. While we know the answer RL should be equal to Rg for maximum power transfer, unfortunately what you can see is that there is a transmission line in between, right. So, because there is a transmission line with a characteristic impedance of Z0, or in the lossless case this simply becomes equal to R0, and there is a certain length L, the impedance seen looking into this point, the impedance will be complex in general. This impedance seen looking at the input terminals of the transmission line will not be equal to Rg. So, therefore, there is no maximum power transfer that would take place in this condition. However, we are designing the transmission line, so we are very well free to choose whatever length of the transmission line that we want and whatever the value of R0 that we want. Let us see what we can do by choosing these two parameters in order to make the input impedance seen here at the input terminals of the transmission line to be equal to RL. Okay. We can do that very easily by considering L equal to lambda by 4, because when you take L equal to lambda by 4, the input impedance or the impedance seen looking into the transmission line of a length lambda by 4 will be equal to Z0 square by ZL, okay. Or for the real case that we are considering, this would mean R in, the real part of Z in will be equal to real, in this case R in will be equal to R0 square divided by RL. But please note that this is only R in, the impedance seen looking into the transmission line and the load, okay. If we somehow make this equal to Rg, then we have achieved our operation. Why? Because in the normalized case that you look at, right, or in the case that we have looked at, Rin will be equal to Rg, or if I divide this R0 onto this side, I see that the normalized load Rg by R0 must be equal to 1 by RL by R0, right. So, the normalized impedances, source impedance, must be equal to 1 by normalized load impedance, okay, or load resistance. But 1 by normalized load resistance is nothing but admittance. And how do I go from impedance to admittance? I need to use a quarter wave transformer, or I need to use a quarter wave length transmission line. So, this is the reason why this is called as quarter wave transformer, because it transforms RL into 1 by RL, and when you choose R0 equal to square root of RL into Rg, then you are done. Then you are essentially ensuring that this Rin is equal to Rg, but Rin equal to Rg simply means that RL will now be equal to Rg. Why? You can substitute R0 square with RL Rg here, RL cancels and Rg will be equal to Rg. So, in other words, if I use a lambda by 4 transmission line, then no matter what resistive load RL that I connect, I can transform that into seen to look into Rg by suitably varying Z0. So, you fix the transmission line length, okay, you fix the length to lambda by 4, then vary R0 such that if you are matching Rg and RL, you simply have to take R0 equal to square root of Rg into RL. This is why this is called as quarter wave transformer. So let us write this one down. This is a quarter wave transformer or QWT. You might object to this quarter wave transformer because no load will be usually completely resistive and it would be equal to Zg as well. So there is a version in which you can also replace ZL, RL by ZL and Rg by Zg, but that is not very important for us to go into now. But what you would be objecting to is that even if the impedances happen to be real, they will be real only at a particular frequency f0. More importantly, suppose we cannot manufacture length of lambda by 4 either because lambda is large or because there is an imperfection in lambda. So lambda ends up being lambda plus delta lambda. So if the impedances are, or if the length is not exactly equal to lambda by 4, then this entire transformation rule does not work. Okay, it works only when L is equal to lambda by 4. In case your L happens to be some L plus delta L, so this is not lambda plus delta lambda, this has to be L plus delta L, where you go beyond the design lambda by 4 wavelength, then how bad would your system suffer? And you can actually do that one. There is a small calculation that is involved, but I am going to skip the calculation and show you graphically what happens. Okay, so corresponding to a length L equal to lambda by 4 will be a certain frequency f0, because lambda is related to frequency. Lambda is up, where the up is the phase velocity divided by frequency will give you lambda. So at that particular operating frequency, if the line has a length of lambda by 4, then we have seen that perfect matching can be achieved provided L is equal to lambda by 4. So in that case I will have R0 equal to square root of Rg RL, and I would have had maximum power transfer. But if we either change frequency or we change L due to manufacturing constraints, or just because the operating frequency has changed and I cannot change R0 every time or length of the transmission line every time. On a printed circuit board, if I have fixed a track length, track width, track height and everything, then the track is actually fixed. I can't keep changing that one, right? Or even, I mean, there is a solution in the discrete case wherein you can move a tuner, as we would call, but on a printed circuit board with a track length I can't do anything much about that. So in that case, if you move away from L or away from F, then you actually suffer pretty badly in terms of your VSWR. Please remember that VSWR will give you information about the mismatch, because VSWR is directly related to gamma L magnitude or gamma magnitude, and gamma is giving you the information about how much is the incident and the reflected wave are related. So if gamma is equal to 0, there won't be any reflections. So if you look at this case, look at this one for two cases. Let us look at for two cases. When first we assume that the normalized impedance is twice the characteristic impedance, that is 2:1 ratio in which you are trying to match, or you might be trying to match say 4:1 ratio, right. So if the normalized load happens to be about 4, then you see that for the two cases the VSWR starts to worsen, okay, and this is along the frequency or omega or f, okay, the frequency which I am plotting, and this happens to be the center frequency f0, for which the length will be equal to lambda by 4. So if I have chosen this one, and either I am increasing frequency or I could be increasing L, so both qualitatively give you the same answer. In fact, quantitatively also they give you the same answer. So this case, which is the one that we have written, is for the case of 4, and for the case of 2:1 impedance matching ratio, this would be the scenario, okay. So this is for the case of RL equal to or RL bar equal to 2. So you can see that the larger the impedance mismatch that you are trying to match, the smaller will be the corresponding bandwidth. What is bandwidth? If I move slightly away from omega 0 or f0, or if I move slightly away from the design length L, either by increasing the length or by decreasing the length due to manufacturing constraints, my VSWR shoots up. Any VSWR above 1.5 is typically considered to be very bad, okay. I will give you as an exercise in the sheet. You can actually calculate at what frequencies these VSWR curves hit 1.5. So starting from the minimum value of 1 at the design wavelength, they will quickly hit 1.5, and you see that the larger is the impedance ratio, the smaller is the bandwidth. The bandwidth is slightly better when your impedances are of the same order in which you are trying to match. So, this is how bad the quarter wave transformer does as you move away, and you will have an opportunity in the tutorial sheet to actually perform all these calculations using MATLAB and plot this VSWR as a function of the operating frequency f. Despite the fact that VSWR increases, we still use quarter wave transformer, not in a single section quarter wave transformer, but multi-section quarter wave transformers. The reason why we do that is because if you calculate what is called as the transducer loss in dB, I will not derive this expression. So, if you calculate the transducer loss, again you can write a short MATLAB code in order to do this thing, you will see that no matter what the value that I am trying to match, if I get the transducer loss, right, I am actually okay even with a poor transformer, because if I do not use any transformer, the transmission loss will be much more than I using. So, even a poor quarter wave transformer, poorly designed, poorly implemented quarter wave transformer will still be some sort of an improvement over using no impedance matching at all. Okay. This does not mean that you should go and design a poor quarter wave transformer. It simply means that even if by some problem the quarter wave transformer is not very good, turns out to be poor, there is still merit in using this quarter wave transformer for impedance matching. We now go to another technique of impedance matching in which we are going to use a transmission line, and this time the design will be done by using a graphical means, that is Smith chart. Okay. Let us first go back to the Smith chart thing. So, this is the Smith chart that we are familiar with. I will draw only a few arcs. Again, it would help in case you are able to get hold of a Smith chart and perform these calculations as I am performing the calculation. So, you will learn a lot when you do that. Okay. So, let us say this is our compressed Smith chart that we have considered, and what we are trying to do here is that suppose I start with a load at some particular point. So, this is the load, or maybe I can try a different load. Let me redraw that arc which I did not put in. So, this is the unit circle. Okay. So, that is the unit circle that I have for the Smith chart, and suppose I am located at this particular point. So, this is the normalized load that I am looking at. So, this is the normalized load. So, going back to the circuit itself, I am at the transmission line terminals connecting to the load, and I know the characteristic impedance of the transmission line, which I have already designed to be equal to Z0. Okay. And I normalize this load, so that normalized load is ZL by Z0. Okay. Now, watch what happens as we move towards the generator, that is away from the load. What happens on the transmission line? My impedance keeps changing at every point. Remember, the impedance at any point on the transmission line is the line impedance, and this is some Z0, ZL plus J Z0, something that we have already talked about, right. So, the impedance continuously changes. While it is continuously changes, at some particular point, okay, the impedance might be in such a way that you would hit 1 plus Jx. When you hit 1 plus Jx, then you can actually stop, you can cut this transmission line, replace this transmission line portion onto this left hand side by a reactive, by a transmission line which is terminated with something, and then give you a reactance of minus Jx, such that when you move past that plane, the total impedance seen here will be equal to 1. And of course, this is normalized, therefore, you should remember that this is normalized impedance equal to 1, which means that I have matched my ZL to Z0. I do the same operation at the transmitter end also. The only problem that you would see with this is that you have to cut your transmission lines, and that is not always an easier option to cut, nor that is something that you would like to do on a printed circuit board, for example, if you are implementing this. Even on an otherwise, it is actually a little difficult to cut something and then replace something in the series. So, this solution, although is very nice, we do not normally look at that. Instead, what we do is we recognize that a Smith chart is as good as an impedance chart, as good as it is a admittance chart, right. So, what we do now is we simply realize that I can work with admittances. So, I instead of talking about ZL bar, I talk about YL bar at the load side, and then I move YL bar. So at some point, at some plane when I land, I would have obtained YL bar prime, that is the transformed admittance, which will have a real part equal to 1, but some imaginary part equal to JB, okay, where B is the susceptance. So I have actually moved it in such a way that I am landed on the transformed admittance of 1 plus JB. So when I do that, right, I can at this point connect a stub, because the stub admittance seen looking at this admittance, if I am able to manage that to be equal to minus JB, right, the stub could be either short circuited stub or could be an open circuited stub, okay, does not matter, whichever it is, depending on the application you might choose one over the other, okay. So if my stub provides an admittance of minus JB, pure reactive admittance of minus JB, then the total admittance seen after including this stub, which is connected in the shunt, this is called as a stub being a very small transmission line which I have connected in parallel, okay. So because of this parallel thing, I am adding admittances. In the series the stubs add impedances, but in parallel they add admittances. So when I add admittance of minus JB, the transformed normalized admittance will simply be equal to 1. That is, you have achieved a condition that YL bar is equal to Y0. The impedance seen looking at this point on the transmission line is equal to the admittance Y0, the characteristic admittance of the transmission line, and most importantly, you did not have to cut any transmission line. You just have to take this point and connect a short stub, and you can do this very well even on a printed circuit board. So on a printed circuit board, let us say this is the track that is going around, then you can actually take a track and then create a via of an appropriate length, or create a track of an appropriate length and then do this. Of course, in a PCB you can even, since you are doing it not on the dynamic case, you can even do the series stub, but on a antenna tuner for example, right. So suppose say this is my antenna and these are the antenna lines that are connected maybe to the TV set, not in the this one. So here I can put a tuner, okay, which will connect from these two lines a short circuited stub or an open circuited stub, and you can simply move the tuner, okay. Why do I need to move the tuner? I need to know what is the distance over which I have to move from the load to the point where I reach YL prime. So if I move from the load, this is the load, if I move a distance of D, then I would have reached YL bar, which is 1 plus JB. Then if I adjust the length of this one, there are adjustable shorts available, that is why you normally see this one with the short circuited stubs. So this adjusted stub shorts will give you a length, or the length of the stub let us say is about L, okay. That L should be chosen such that you get a admittance of minus JB, okay. If B happens to be positive here, then you need a minus JB. If B happens to be negative, then you need a plus JB, okay. Let us see how this entire thing works. So we started off with the load here, and what do we do in order to find out the admittance? In order to find out the admittance, we need to first draw the SWR circle. So this is the SWR circle that I have drawn, and then start moving towards the generator, right. I am away from the load, I am moving towards the generator. So I keep moving. Before moving, I should first find the admittance. So to find the admittance, I need to, after drawing the SWR circle, I need to locate a point opposite, okay, so that I start with the admittance over here, okay. So this is my YL bar, this was ZL bar. Now I start moving, not from here. So let me draw this once more, okay. So let me draw this once more, give me a couple of minutes. So you can see that I am again drawing the Smith chart. The basic idea is you start with the load and then you transform the load, okay. So you transform the load into a admittance load. So this is one more circle, okay. Now we are good to go. We start again with a load here and then correspondingly draw the SWR circle. Does not matter what the load value is, we will give you the numbers later for you to practice, but start with the SWR circle. You can clearly see that this is the circle that I have drawn, and from there locate the diametrically opposite point which will give you the admittance. So this is your admittance YL bar, okay, and this is your point where you have started off with the load ZL bar. After you have come to the admittance, you start moving towards the generator, that is you keep moving away from the load. At some point you will actually end up meeting this unit circle, right. So on the unit circle, what is your admittance? On the unit circle, the admittance is actually equal to 1, the real part of the admittance is equal to 1. So if you look at the intersection of this SWR circle with the unit circle, let us mark that point as, say, maybe a black point over here. So this point, right, is the point where the impedance is YL prime, okay, and the distance that you had to move in order to reach this point is simply the distance d on the transmission line that you have moved. So you started off with YL bar, you reached YL prime, which is given by the intersection of the SWR circle with the unit circle, okay. Of course, if you continue your journey, you would reach one more point here, in which case you would have you can consider this as a second solution, this as a first solution, okay. First solution you are at a distance of d. For a second solution, you would have to cover an extra distance, okay, an extra distance of, say, d prime. So that solution 1 is at a distance d from the load, okay, whereas solution 2 will be at a distance of d plus d prime from the load, okay. We will not consider the second solution, it is more or less that whenever you want to place a stub, you want to place the stub as close as possible to the load. Therefore, you usually are okay with the first position itself. So once you have reached this position, okay, which is YL prime, right, now all that is left is to read what is the value of admittance here, and that would be some 1 plus JB. Here B is positive in this case. So in our case, or in this illustrative case, B is positive, right. So let us say that B is about 0.3, or maybe here it is because inside it is occurring inside the, it is about 0.3, let us say, or 0.5, let us say. What you now need to do is to connect either a short circuited stub, let us assume that we are looking at the short circuited stub of certain length L, such that the reactance here will be minus J 0.5. Please note that this is again the normalized reactance. The actual susceptance is obtained by unnormalizing this one by multiplying it with Y0, okay. So this would be the admittance and or susceptance, and then 1 by susceptance will give you the impedance or the reactance corresponding to this. Anyway, we will not worry about that. So what you need to know, or what you need to do, is to reach minus J 0.5 from the short circuit, right. So either you can actually start from the short circuit point and then move towards the generator such that you reach minus J 0.5, okay. That is actually quite simple. On the Smith chart, when you consider it as an admittance chart, this point will become the short circuit, okay, and you now have to move along the outer periphery because there is no imaginary part for the admittance. The imaginary part of the admittance is 0, so which happens to be on the outer circle. So you keep moving from the short circuit point on the varying reactance circle, that is on the outer circle, such that you hit about minus J 0.5. So let us say that happens about at this point, okay. From here you draw a circle and note down on the WTG scale what is the value here, and this difference, this is the distance which you have covered from the short circuit towards the generator, which will give you the length of the transmission line that is necessary in order to add a susceptance of minus J 0.5 or minus JB. So that once you have found the length as well as the distance at which the stub is to be placed, in this example we considered the stub to be short circuited, but you could consider an open circuited stub, in which case you will actually start on this side and then move towards the generator, okay, right. So that is what you would do, and when you do that you will end up with the solution which is correct for the open circuited stub, okay. So depending on what kind of a stub that you employ, you can obtain the appropriate length of the stub which will allow you to add the required amount of susceptance, okay. There is one small catch here. Suppose someone tells you that the characteristic impedance of the stub has to be different from the characteristic impedance of the main transmission line. That is, the stub has, say, Y0 prime while the main line has some Y0. In that case, what you do at the point where you find out what is the reactance, right. So this is the amount of susceptance that you need to add by the stub, right. So if it was plus JB, you would have added minus JB into Y0, that would be the unnormalized susceptance that need to be added. So this unnormalized susceptance you divide by Y0 prime, which is the stub line characteristic admittance. So when you divide this, you will end up with a new normalized B. So, I mean B or B prime, that would not be equal to the original B, but it would be y0 divided by y0 prime, where this ratio will tell you what should be the value at which you have to scale the plus j 0.5 term, right, the 0.5 being the B value, which was the residual susceptance if you think of. How much you should scale this 0.5 or B value is given by the ratio of the characteristic admittances of the main line to the secondary transmission line or the stub line. This completes our impedance matching with stub or with a shunt stub, as we would call. This is, we have used only one stub. In practice or in olden days you could still use you could use multiple stubs. So, there were 2 stubs, 3 stub tuner, even 5 stub tuner was available for impedance matching using these stub cases. These are all parallel or shunt stub matching cases. You can even have stubs in the series, but the problem is you have to cut the transmission line. So far we have considered impedance matching with distributed or transmission lines. In the next module we will consider impedance matching with a lumped element circuit. Thank you very much.